Hi everyone, welcome to the video lesson for Tuesday, April 6th and Wednesday, April 7th. Welcome back from spring break. I hope everyone had a restful and a very relaxing spring break, but it's time to get back into chemistry. We started off with our warm-up, which helped us review some of the things that we learned right before spring break. Then we added one more note slide to our Part 1 notes of Unit 7. Then we started our Part 2 notes of Unit 7, all about bond energies. Your homework tonight is to take your first attempt of that thermo quiz. Now remember, I did unlock it before spring break if anyone wanted to get ahead, but now I'm officially assigning it, so make sure you get that first attempt in this week. Your second attempt will be unlocked on Thursday, but I really want to encourage you that if you don't like your first grade, please come in and meet with one of your teachers before you do your second attempt. Let's talk it over. Let's make sure you understand why you got the questions wrong, so you do better on your next attempt. You also have your reaction energy gizmo that is also due this week. So your warm-up today was 2 fill-in-the-blank questions. I asked you, breaking bonds blanks energy and forming bonds blanks energy. So there was more than one correct way to answer this. Breaking bonds require energy. Breaking bonds absorbs energy. Just remember that when I'm in a bond, my 2 atoms are usually pretty stable. So if I'm going to break them apart, I have to give them a reason. I have to put energy into those atoms so they vibrate and they move so much that they're no longer attached to each other. So breaking bonds requires energy. It is endothermic. Now, forming bonds is exothermic. Forming bonds releases energy. It loses energy. When I form a bond, I've got 2 pretty high energy atoms that calm down enough to get close enough to form a bond. So anytime I go from something that's kind of not so stable to something more stable, I have to release energy. It's like those electrons that we learned about last semester. You gave them energy, they got excited. In order to become more stable, to go back to the ground state, they released that energy. Same thing happens when I form a bond. I become more stable, so I release that energy. The first link in your Week 9 module takes you to the extra note slides for Unit 1. Remember, I highly recommend that you Control-C and Control-V to copy and paste these slides into your Unit 7 Part 1 Google Slide Notes. A catalyst is something that speeds up a reaction by lowering the activation energy. So if you remember from Part 1, all reactions require energy, the activation energy, before it can actually take place. I can have a match. Matches are very good at combustion, but I can stare at a match all day and it won't begin that chemical reaction of combustion until I strike it against a box. I need to add energy to start breaking those bonds before they're going to start making new bonds and giving off energy as they form new bonds. So a catalyst lowers the amount of energy you need in order for a chemical reaction to occur. Because you need less energy to get these bonds to start breaking, you can have a chemical reaction take place faster. The second slide in this additional slides was a YouTube video that we watched earlier in the year about how to speed up rates of reaction. The link in your slide starts right at the catalyst part. You can also rewatch the entire video if you would like. The next link in your Week 9 module will generate a copy of our Unit 7 Notes Part 2 in your Google Drive. Remember, as soon as this loads into your Google Drive, please click that little folder that says Move and move this into a chemistry folder so you can more easily find your notes. In Part 1 of our Unit 7 notes, we looked at graphs and we theorized how you could find the change of energy, delta H, by looking at values on a graph. Well, now we're actually going to have you use an equation to solve for delta H using the energy that is used and released from the making and breaking of bonds. So delta H, my change in heat, is equal to the energy absorbed by my reactants in order to break their bonds minus the energy released by the new bonds that are being formed in a reaction. My bond energy is the amount of energy that's required whenever I want to break a bond, or the amount of energy I get when I make a bond. Now, the important thing here is that it doesn't matter if I'm making or breaking a bond. It's the same amount of energy. If I have two oxygens that are single bonded together, the amount of energy it takes for me to break those two oxygens apart is the same amount of energy I will get if I bond two oxygen atoms together for a single bond. Now, by a particular bond, I mean any two different types of elements and a single, double, or a triple bond. So two oxygen atoms that are single bonded will have a particular amount of energy, but a hydrogen and an oxygen that are single bonded together will have a different amount of energy. You will never need to memorize the different bond energies. I will always provide you a reference table. Now, the larger the bond energy is to break or that you will receive from a bond is proportional to how strong it is. So stronger bonds have larger bond energies. Therefore, double and triple bonds have more energy than single bonds. A single bond between two carbon atoms has about 348 kilojoules. But a double bond is going to have more energy, almost double, a little bit less than double, about 612 kilojoules of energy. This is important because a double or a triple bond is going to have a different energy than a single bond. So when you're looking up your bond energies, make sure you're choosing the correct type of bond. And once everything is said and done, after you've taken that energy absorbed to break bonds and subtracted the energy released from forming bonds, your resulting delta H tells you what type of reaction you had. Anytime you have a negative delta H value, you had an exothermic reaction. Anytime you have a positive delta H, you had an endothermic reaction. So I've rewritten the equation from that first bullet point below. Delta H is equal to your reactants minus your products. Now, something that I find helps a lot of students understand this a little bit better is if we think about this like money. Imagine delta H, instead of being a change in energy, was change in your bank account. Those reactants, the energy that you put into a reaction, would be the money you earned from a job, and the products, the energy released from making bonds, would be kind of like money that you spend. So if I make $100, but then buy $50 worth of chocolates, my delta H would be positive $50. I will have spent half that money that I earned. So there will be a positive value. Money went into my bank account. But if I earn $50 and I spend $100, then the change in my bank account would be negative 50. Money will have exoded my bank account. So here are the steps you need to follow in order to calculate for delta H with bond energies. The first thing you need to do is identify all the different types of bonds in your reactants and then in your products. Look at those Lewis dot structures. Each time you have two different types of elements that are bonded together, you have a different type of bond. Then you need to count how many of each of those types of bonds exists on either side of your reaction. Once you know what bonds you have and how many you have of each, you can multiply the number of bonds by its bond energy. And again, you find your bond energy in a reference table. I will never expect you to have them memorized. Then, add up the total amount of energy that goes into your reaction and the total amount of energy that comes out from your products. Then, take the total energy released from your products and subtract it by the total amount of energy absorbed by your reactants. So once again, your equation that you're going to use is delta H, your change in energy, is equal to the energy of your reactants minus the energy of your products. So here on slide 4, we have our first example problem. Find the change in energy, delta H, for the following reaction. H2 plus Br2 yields 2 HBr. So I've got my Lewis structures all ready for me. So my first bond that I notice is H bonded to H. So I'm going to come down here and I'm going to put that in the first box. I only have that particular bond one time. Then the next one I see is Br bound to another Br. So I'm going to put that in my table. I only have that type of bond one time, so there's only the one. Then I'm going to go over to my product side, and the first bond I see is H bonded to Br. And notice in HBr there is only one bond, but I got 2 HBrs from my reaction. So there's one H bonded to Br here, and there's another H bonded to Br there as well. So on my product side, I have H to Br, and I have 2 of them. So now I know which types of bonds I have and how many. Let me look up their bond energies. So hydrogen bonded to hydrogen, whether I'm making or breaking that bond, is going to involve 436 kilojoules per mole. So I have 436 kilojoules per mole times my one bond. So a total of 436 kilojoules is going to be used to break the bond between my 2 hydrogens. Next, my bromine attached to my bromine. Breaking that bond is going to require 196 kilojoules per mole. So 196 kilojoules per mole times 1 means a total of 196 kilojoules per mole will be used to break apart my bromines. Then on my product side, I have hydrogen bound to bromine. So creating that bond is going to produce 366 kilojoules per mole. So I'm going to take its bond energy, and I have 366 times 2, because remember, I have that bond twice in my reaction, for a total amount of energy of 732 kilojoules that's going to be released. So now I want to add up my totals. So 436 kilojoules per mole plus 196 kilojoules per mole means I'm going to put in a total of 632 kilojoules to break all these bonds. Then on my product side, I have 732 kilojoules being released by my new bonds. So 632 minus 732 means that my overall change in energy, my delta H, is negative 100 kilojoules per mole. Since this is a negative number, that means more energy has left this reaction than has been put into it. Think of this like a bank account. If you make $632 and you spend $732, $100 left your bank account. It exited your bank account. Anytime you have a negative value for delta H, it means you have an exothermic reaction. On the next slide, I gave you some time in class to work on this on your own, to go through those same steps to solve the problem. Remember, the first thing you want to do is identify the different types of bonds. So if I look at the Lewis structures of my reactants, the first one I notice is carbon bonded to a hydrogen, and I have it 1, 2, 3, 4 times over here on my reactant side. So carbon to hydrogen, and 4 of them. Next, I notice I have a carbon to carbon double bond right there. It's the only one. So I've got carbon to carbon double bonded, and I only have 1. And still over here on my reactant side, I also have a hydrogen single bonded to another hydrogen, and I only have the 1. Now on my product side, I see, oh look, that hydrogen to carbon bond again. So on my product side, I have it 1, 2, 3, 4, 5, pop, pop, 6 times. So I have carbon to hydrogen 6 times. And there's one more there. My carbon is bound to another carbon, but this time with a single bond. And I only have 1 of those. Now I need to look up the bond energies for these different types of bonds. So first I have carbon to hydrogen. So it takes 413 kilojoules to make or break those bonds. So over here on my reactant side, I have 413 times the 4 bonds that I have is equal to 1,652 kilojoules per mole. On my product side, I have that same bond. So 413 times 6 bonds total gives me a total of 2,478 kilojoules per mole. Next on my list, I have carbon double bonded to another carbon. So that's going to use or give a total of 614 kilojoules. So 614 times 1 means I'm going to put a total of 614 kilojoules into this reaction just to break that bond. A hydrogen to hydrogen bond has 436 kilojoules of energy. I only have the 1. So 436 times 1 gives me 436 kilojoules per mole. And lastly, I have a carbon to carbon single bonded, and those require 348 kilojoules to break, or will release that much. So 348 times 1 gives me a total of 348 kilojoules per mole. So if I add up all of the energy that goes into my reactants to break those bonds, I get a grand total of 2,702 kilojoules. Then I'm going to add up the grand total of all the energy that's being released by the formation of these new bonds, and I get a total of 2,826 kilojoules per mole. So now I just need to subtract them. So 2,702 minus 2,826 leaves me with negative 124 kilojoules per mole. So more energy left this reaction than went into it. So this is an exothermic reaction. Now in class, we did not have enough time to go over this example, but I strongly encourage you to try this on your own. But we have the same process. I need to find all the different types of bonds. So the first one I see here is that hydrogen to carbon again. I have it 1, 2, 3, 4 times on this side of my reaction. So carbon to hydrogen 4 times. Next, I have a chlorine bonded to another chlorine. I only have that type of bond 1 time. That's everything that's bound together on my reactant side. So now I go to my product side, and oh, the first one I notice again is carbon to hydrogen. So I've got carbon to hydrogen, and on this side I have 2 of that bond. Then the next bond I see is chlorine bound to carbon. I have that type of bond 2 times. And then I also have a hydrogen single bonded to another hydrogen, and I only have that 1 time. So I know what bonds I have and how many of each type of bond. Now I need to look up their energies. So carbon to hydrogen is still 413 kilojoules per mole. And notice, here I wrote it as carbon to hydrogen, here it's hydrogen to carbon. It doesn't matter what order you write your 2 elements in. It really doesn't, because what we care about here is just what 2 elements are attached to each other. Because here I've got hydrogen attached to a carbon, but I also have a carbon single bonded to another hydrogen. So it's the same thing on either side, so it doesn't matter what order you write it in. So over here on my reactant side, I have 413 times those 4 bonds for a total of 1,652 kilojoules. And on my product side, I have 413 times there's only 2 carbon to hydrogen bonds this time, for a total of 826 kilojoules that will be released from making those bonds. Next, I have my chloride bonded to a chloride. So that's going to be 243 kilojoules to destroy each of those types of bonds, times 1 means I'm going to use a total of 243 kilojoules to break those bonds. Back to my product side, I next have a carbon to chloride bond. So that's going to release 330 kilojoules for each bond that makes. I have 2 of them. So 330 times 2 means I will get a total of 660 kilojoules per mole. And lastly, I've got hydrogen single bonded to another hydrogen. I only have 1 of those bonds. So 436 times 1 means I'll get a total of 436 kilojoules per mole of those new hydrogen bonds. Now, I want to add up the totals on either side. So 1,652 plus 243 gives me a grand total of 1,895 kilojoules that will go into this reaction to break all of those bonds. Then on my product side, 826 plus 660 plus 436 means a grand total of 1,922 kilojoules is going to be released by this reaction. So 1,895 minus 1,922 means my delta H, my change in energy, is negative 27. So that makes this another exothermic reaction. So those are all the notes and examples we went over today in class. Don't forget to do your homework by this Friday. Also, check Synergy. Your grades have been updated since spring break. Make sure you've got all of your work in and you're not missing any checkpoints. I noticed quite a few students were missing quite a few checkpoints. That's going to be hurting your grade a lot. Well, until I see you guys again on Thursday and Friday, stay safe and make good choices.